Have you heard that nitrates in meat are toxic and even cause cancer? These days, concerns about meat often focus less on fat and more on chemicals, especially nitrates and nitrites. But how much of that worry is actually supported by science? Here's what might surprise you. The biggest source of nitrates in your diet probably isn't meat. It's vegetables. Spinach, beets, celery, they are naturally rich in them. Your body converts those nitrates into nitric oxide, a molecule that improves blood flow, supports mitochondrial function, and enhances insulin sensitivity. So why the concern? It's not the nitrate itself, it's the context. Under certain conditions and with specific chemical pairings, nitrates may form harmful byproducts, but that risk depends on many factors, and the evidence, especially in humans, is far from clear. In fact, some research suggests that nitrates might actually be beneficial, particularly when they come from whole foods. Before we fear the chemical, maybe we should understand the chemistry. This is Lecture 109 of the Metabolic Classroom. Looking to improve your own metabolic health? Visit InsulinIQ.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more. Welcome back to the Metabolic Classroom. I'm Benjamin Bikman, biomedical scientist and professor of cell biology. Today we're discussing a topic that's often misunderstood and even feared, that is nitrates and nitrites. In recent years, much of the public concern around meat consumption has shifted from saturated fat and cholesterol to something a little more elusive, these chemical additives. Now, among these things that have been added to meat, nitrates and nitrites have become central villains in this narrative. They're very often cited in headlines and documentaries as the reason processed meats are toxic or carcinogenic. For many people, the fear of meat is really a fear of the chemicals used to preserve it. But how much of this fear is justified? Are these compounds truly harmful, or are they simply misunderstood? But here's the twist to make it even more complicated. What if these same compounds, so often feared, actually offer some pretty substantial metabolic benefits? What if they support mitochondrial function, insulin sensitivity, and even fat metabolism? Well, today we are going to unpack the biochemistry, the history a little bit, and most importantly, the evidence both for and against these compounds. After all, if we're going to make informed decisions about our food, we need more than fear. We need some facts. So let's explore the science. And in doing so, let's just get started with a definition of the compounds of interest. Nitrates and nitrites are naturally occurring ions composed of nitrogen and oxygen. You'll find them in soil, water, many foods, especially vegetables, and yes, cured meats. In our bodies, nitrates can be converted to nitrites, and nitrites can further convert to nitric oxide, a molecule that is very important and helpful for vascular health. So these aren't foreign chemicals, they're very much a part of our biology. Now, how are they used in food? Because that is the main reason and instance where people fear them. In processed meats, nitrites are used to prevent bacterial growth, especially botulism, or the bacteria that leads to that infection. Now, they also can help preserve color and even flavor in meat. So it's easy to see why people would use them. And indeed, the reasons are so obvious that people have been using them for centuries in meat preservation, though people didn't always perhaps know what they were working with. Historically, meat preservation began with salting, a practice that predates even written history. Ancient civilizations like the Sumerians, Greeks, Romans used salt to draw moisture out of meat and inhibit the spoilage of the meat. But a twist here is that the salt that they often used would, of course, come from natural sources like rock salt or evaporated seawater. And all of these contain natural impurities, most especially potassium nitrate, also known as saltpeter. Around 850 BC, during Homer's time, this potassium nitrate was already being used to preserve meat. The Romans noticed that certain salts gave meat a reddish color and better flavor, and that color, we now know, came from nitric oxide, a product of nitrate and nitrite reactions with meat proteins like myoglobin. In the Middle Ages, this nitrate was widely used in meat curing across Europe. Monasteries and butchers used it to preserve meats like ham and bacon. It wasn't until the late 19th and early 20th centuries that scientists identified nitrite as the active compound responsible for the color and the preservation effects that people were looking for. So while ancient people didn't know they were using nitrates and nitrites, they were, thanks to the natural chemistry of the salt sources they had. It is, in fact, a great example of traditional practices aligning with what we now know. All right, now that's how it was used historically, but are those the only sources? In fact, no, far from it. Vegetables are actually the largest source of dietary nitrates in the average individual, up to 80%. Foods like spinach and beets, lettuce, and celery are very high. And in fact, processed meats contribute only to about 5 to 10% of dietary nitrate, and then maybe about half of all of the dietary nitrites. Water can also be a source, although that really depends on the area. But what this all means is that, ironically, the foods most associated with health, like leafy greens and vegetables, are actually invariably and even unavoidably the most rich sources of these nitrates. So let's now talk about the health concern. Although I want you to keep in mind the source, that again, the vast majority of nitrates and even nitrites that we're getting are coming from vegetables. All right, now what are the health concerns? The concerns with nitrates and nitrites largely focus on their potential to form nitrosamines. These are compounds that are known to be carcinogenic in animal models. So in other words, nitrosamines can promote cancer in animal models. And these nitrosamines can form when nitrites react with amines, particularly in an acidic environment like the stomach. And heme iron, which is certainly a component of red meats, is thought to enhance this reaction. And so here is the overall proposed mechanism. Nitrites, when combined with dietary amines and heme iron under acidic conditions, can form nitrosamines. And then these compounds can damage DNA and therefore promote mutations, as the theory goes. That, those mutations on DNA are thought to be a hallmark and essential component or factor in the development of cancers. Additionally, the heme iron is thought to be a little more relevant because of its potential to promote the synthesis of reactive oxygen species, which can further promote cellular damage. However, it's critical to emphasize that this mechanism has been demonstrated in animal models and in cell culture work. In humans, the evidence is entirely correlational. To say that all another way, there is no evidence in humans that these things happen. It's all correlational. Now let me get into that a little bit, just for the sake of being thorough. One example is the Nutrinet Santé cohort study. This study found associations between nitrites from food additives and increased prostate cancer risk. But again, as you're going to hear me repeat often, this is an observational study, meaning it cannot establish causation. Confounding variables like overall diet quality, lifestyle, and even genetic predisposition can heavily influence the results. Importantly, other studies have failed to find a consistent link. A 2011 meta-analysis by Lowe et al., and again, remember, to get access to all the citations, consider being an insider. But this study in 2011 found that while processed meat intake was associated with colorectal cancer, the effect size was very modest and confounded by other dietary and lifestyle factors. And when it comes to heme iron specifically, that's important to focus on because it's thought to be a critical reason why the nitrates in meat are somehow so much more harmful than the nitrates in vegetables. So with the heme iron, large cohort studies have found no consistent association between heme iron intake and cancer risk. For example, data from the EPIC, that's an acronym, EPIC cohort, and Mendelian randomization studies show no causal relationship between heme iron or processed meat intake and most cancers, including breast, prostate, and kidney cancers. So while the biochemical mechanism is plausible, and I'm happy to admit that as a scientist, there is a series of events that could connect these chemicals from meat to the additives in processed meats to cancers, but the real world evidence in humans is far from conclusive. In fact, it is not conclusive at all. The context, like what else is in the food, how much is consumed, and perhaps the overall dietary pattern matters immensely. And this is something I'm going to revisit in just a little bit, and namely the confounding variables to help us make sense of some of the human evidence. Now, let's shift our focus from risk to potential benefit, because the story of nitrates and nitrites isn't just about what might go wrong, it's also about what might go right. These compounds are increasingly recognized for their physiological and metabolic advantages. Far from being inert or harmful, they participate in critical biochemical pathways that support health. Now, I'm going to go through several reasons. So, firstly, importantly, these compounds are not just passing through the digestive tract. After ingestion, so after you eat them, nitrate is rapidly absorbed. It's concentrated in the saliva and converted to nitrite by oral bacteria. Nitrite is then swallowed and either converted to nitric oxide in the stomach or absorbed into the bloodstream. Plasma nitrate and nitrite levels rise significantly after a nitrate-rich meal, confirming their systemic bioavailability. So to sum all of that up, when we eat nitrates, we absorb them, we convert them to nitrite, and then that nitrite is readily converted into nitric oxide. So let's talk a little bit more about nitric oxide, because at the heart of this story, it sits there as a critical signaling molecule. Nitric oxide's most famous effect is to regulate blood flow, but it also is involved in mitochondrial function and even some cell-to-cell communication. Dietary nitrate is converted to nitrite and then to nitric oxide, like I mentioned earlier. This pathway is independent of the classical nitric oxide synthase NOS system, making it especially important in hypoxic tissues like exercising muscle, or even, as we'll get to, inflamed or suffocating or hypoxic adipose tissue. The nitrate, nitrite, nitric oxide pathway is also critical for vascular health. Nitric oxide promotes vasodilation, so making the blood vessels expand and become wider. Naturally, this means that blood is going to flow more easily and blood pressure is going to go down. This is particularly relevant in people with endothelial dysfunction. These effects are well documented in both healthy and hypertensive populations. So let me just reiterate this. This is, in fact, a known physiological phenomenon in humans. The nitrate can increase the levels of nitric oxide, which can induce, albeit perhaps a modest degree of vasodilation, but in real time actually lower blood pressure. Now let's talk about mitochondria, an area of research for me as a scientist. In fact, you'd be hard-pressed to find a paper I've published in the past 10 years that doesn't focus on some aspect of mitochondrial bioenergetics. And even here, it's a very relevant topic. One of the most consistent findings is that dietary nitrate improves mitochondrial efficiency. Now, what do I mean by that? In the landmark study, healthy volunteers who consumed nitrate-rich beetroot juice, but remember, this is the same nitrates that is coming from processed meats, but they found that there was a reduction in oxygen cost during exercise and an increase in ATP production per oxygen molecule consumed. Now, that might have sounded a little technical. This suggests that nitrate enhances the coupling of oxidative phosphorylation, essentially making the mitochondria more efficient. You've heard me discuss this abundantly, this idea of mitochondrial coupling, where the mitochondria are breaking down nutrients in a way that it is more effectively producing ATP. Or in some instances, the mitochondria will be more uncoupled, wherein the mitochondria are just wasting energy And it's not necessarily burning energy to create ATP. Now, that can be a good thing sometimes or a bad thing. It is not a good thing when it comes to exercise. And that was part of the context here that they looked at in this human study, that they found during exercise, the consumption of the nitrate-rich supplement ended up improving mitochondrial efficiency. That would suggest you're getting a little more energy produced as you're burning fuel sources like glucose or fats. But of course, it's hard for me to get through any topic without bringing up insulin sensitivity. But even here, emerging research suggests that dietary nitrate and nitrite may play a supportive role in regulating blood glucose and improving insulin sensitivity. In animal models of type 2 diabetes, nitrite supplementation has been shown to lower fasting glucose levels and improve glucose tolerance. These effects are believed to occur through several complementary mechanisms. One of them is a pathway that involves the enhancement of blood flow to the pancreas, which improves insulin secretion. This would, of course, be relevant in people who have a deficiency of insulin, which is not overly common, but it could be occurring in some individuals in late-stage type 2 diabetes. But perhaps more interesting, nitrate and nitrite also activates a signaling molecule inside the cells called cyclic GMP. This molecule is produced when nitric oxide stimulates an enzyme called guanylyl cyclase. So nitric oxide will activate this enzyme that will result in the production of cyclic GMP. Cyclic GMP is actually a kind of close relative to ATP, but rather than acting as an energy source like ATP does for the cell to get work done, cyclic GMP actually it works as an activating or a signaling molecule because it will activate a protein kinase called PKG or protein kinase G. And then PKG is the part of this whole busy pathway that actually comes back to insulin. In the context of insulin signaling, cyclic GMP, which then activates protein kinase G, PKG, appears to enhance the activity of the insulin receptor. This then means that when insulin comes and binds to its receptor, if you've had cyclic GMP and then PKG activated, that pathway, the downstream effects, including GLUT4, which is going to be that transporter that goes into the cell membrane to move glucose in, it's going to work better. In other words, the cell, and the body by extension is becoming more insulin sensitive. So all of this busy pathway, starting with nitrate and ending with insulin, is just a way that explains how nitrates can actually improve insulin sensitivity. But it doesn't stop there. Cyclic GMP, beyond its effects on insulin signaling, also has an effect on anti-inflammatory signaling. This, of course, is very important, as you've heard me explain previously. Inflammation is one of the three primary or cardinal causes of insulin resistance. And the data are pretty compelling. There are some rodent studies finding that if you remove the signaling of cyclic GMP, so in particular mice lacking this cyclic GMP dependent event show impaired blood flow, elevated blood glucose, elevated insulin resistance, and demonstrable increases in inflammation. So all of this just shows the relevance of this pathway. And again, nitrate can activate it all, how important it all is in metabolic health. Now, you would say, well, Ben, most of the studies you were just citing is coming from animal work. It is, although some of what I have mentioned is, in fact, from human. But remember, it's also that animal work that is used to justify the vilification of nitrates in the first place. We're not relying on human data in those instances. We're relying on animal data. So if you will, I'm fighting fire with fire. But altogether, these findings certainly suggest that nitrate and nitrite may help restore insulin sensitivity through both changes in vascular physiology, the blood vessels, as well as some intracellular mechanisms, most especially that busy pathway that I described, starting with cyclic GMP. Now, before we leave some of the benefits, I wanted just to mention a very interesting finding in rodent tissue, but particularly with adipose tissue. So these are some rodent studies finding that nitrate can promote the transformation of white fat into the very active mitochondrial uncoupled beige fat. So this is the process we call it beiging, or maybe it's easier to know it as browning, where very low metabolic rate, tightly coupled white adipose tissue turns into a more mitochondrial dense, actually changing the color, making it beiged a little bit. But the mitochondria, in addition to having more of them, have a greater degree of uncoupling. So they're wasting energy. And the nitrates have been shown to actually increase the expression of genes like UCP1, or the uncoupling protein 1. And that is the famous protein that results in the uncoupling of the mitochondria, making them just burn. But also the nitrates can activate PGC1 alpha, which is a critical intracellular signal that stimulates mitochondrial biogenesis. So now that is animal work, but again, we can defend it because it's also animal work that vilifies nitrates in the first place. So we're using animal work to defend from the attacks based on the animal work. Now, none of this is to say truly that there aren't perhaps some risks. Maybe there are risks and they deserve some scrutiny. But in the midst of that, we should consider the potential benefits of these dietary nitrates and nitrites. They do support myriad metabolic benefits like the mitochondrial changes, the insulin signaling, and of course, production of nitric oxide and the vasodilation. In fact, these compounds and the consequences of them are so physiologically relevant and even beneficial that nitrite is being investigated as a therapeutic agent for conditions like heart failure, metabolic syndrome, and even something known as ischemia reperfusion injury, which is a mechanism of a clinical intervention to help people recover from something like a heart attack. So it's time that we certainly stop thinking of nitrates and nitrites as just preservatives or even just overt harms, and recognize them as very bioactive nutrients or chemicals with real metabolic potential. And we absolutely have to acknowledge the human studies, appreciating that there might be a cancer risk, perhaps based on correlational evidence, but that same correlational evidence must bring a degree of caution, because correlation is not causation. Now, having said that, how do we reconcile some of the inconsistencies in the human data? Now, you've heard me discuss this before, that to my great joy, as a basic scientist, I don't have to deal with correlation, which is simply a scientific term for coincidence. I get to deal with causality, where I can do one single thing and note the outcome of that one single thing. While some of these observational or correlational studies have linked processed meats, which have nitrates and nitrites, to an increased risk of cancer, the human evidence is not conclusive. One major limitation throughout all of these human studies is something called healthy user bias. In other words, individuals who avoid processed meat in order to improve their health often engage in a range of known health-promoting behaviors that are sometimes difficult to quantify in a survey. Like they just exercise a little differently or more often. They avoid smoking and alcohol and many other things. They sleep a little better. They have more social interactions or more positive social interactions. And these lifestyle differences absolutely confound study results in correlational findings, which can make it very, very difficult, in fact, I would say impossible, to truly isolate the effects of nitrates or nitrites themselves. Additionally, most studies rely on self-reported dietary data, which is prone to some bias in how they remember things, or just they're considering things wrongly, this idea of misclassification. But even with some of the statistical adjustments, there are just residual confounding variables that will remain, and the associations observed should be interpreted with caution rather than assumed to reflect some direct causality. In the end, nitrates and nitrites are not inherently dangerous. The key is perhaps understanding the context, like the source, perhaps, if things like heme iron may matter, but the dose and perhaps even the dietary environment. But also, frankly, we need to consider the confounding variables that underlie all of the human evidence suggesting a problem in the first place. So before we demonize a molecule, let's just try to look at the bigger picture. Thanks for joining me in the Metabolic Classroom. Until next time, more knowledge, better health. Looking to improve your own metabolic health? Visit insuliniq.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more.